We'll take another example to understand the analytical method of phase plane analysis. Now consider a system whose dynamic equation is governed by the differential equation j theta double dot plus b theta double dot equal to tau j theta double dot plus b theta dot equal to tau. J theta double dot plus b theta dot is equal to tau. Now what we'll choose is we'll choose the state variables for the system, x1 equal to theta and x2 equal to theta dot. That means it is equal to x1 dot. So looking at this equation, from this equation, therefore this equation is j x2 dot plus b theta dot, that is you can say it's x1 dot or x2 equal to tau, which implies x2 dot is equal to tau minus bx2 divided by j. So this is the value of x2 dot. So what we have is x1 dot is equal to x2 and x2 dot is equal to tau minus bx2 by j. So what we will be doing here is first we actually need to solve for x2 dot, and to do that what we will do is we'll equate this equal to z. We'll say this is equal to z, which therefore implies tau minus bx2 by j is equal to z, which implies x2 is equal to tau minus jz divided by b. So from this equation we can get tau minus bx2 by j equal to z. We'll be getting x2 equal to tau minus jz divided by b. So we have now these two equations. We'll differentiate first this equation dx2 by d with respect to time. So dx2 by dt is equal to d tau on the left hand side dz by dt minus j by b times dz by dt, which implies dz is therefore equal to minus b by j times dx2. But what is dx2? dx2 we already know is equal to z. So we can say dz is equal to minus b by j times z. So this gives us dz. Now we will be dividing we have now dz by dt is dz by dt x2 dot is equal to tau minus bx2 by j, that is equal to z. From this we get x equal to tau minus jz by b. Differentiating both sides we get dx2 by dt is equal to minus j by b times dz by dt, which implies dz by dt is equal to minus b by j times dx2 by dt. dx2 by dt we already know is dz is equal to dx2 by dt is nothing but z, so we can directly say dz by dt is equal to minus b by j times z. Now we have actually two equations. One is x1 dot dx1 by dt, which is equal to x2, and we have dz by dt, which is equal to minus b by j times z. So instead of having the variables here, instead of having x1 x2, we also have z here. What we can do after this is we can divide equation 1, you can say, divide it by equation number 2. To eliminate t in this in these two equations, we can divide equation 1 by equation 2. So we get dx1 by dz equal to x2 by minus b by j times z. Now in order to obtain the solution in terms of x1 and x2, which implies dx1 by dz is equal to dx1 by dz is equal to x2 divided by minus b by j times z. What is x2? x2 is this equation, tau minus jz by b. So we get tau minus jz divided by b, and at the bottom we had minus b by j times z, this minus b by j times z. So which implies dx1 is equal to, when you solve for this is tau by b divided by minus b by j z, that becomes equal to minus tau j by b square z, and this dz that was here, I am getting it on the right hand side, so multiplied with dz plus j square by b square, z and z cancels out, this dz on the left hand side will be multiplied here, and it will be d equal to dz. So we have this equation now. Integrating both sides, when we integrate both sides, dx1, integration of dx1 is x1, this is minus tau j by b square, minus tau j by b square, integration of dz divided by z. Integration of dz divided by z will be ln of z plus j square by b square, they are both constants, and integration of dz will be z plus there is a constant above integration, that is c. So we therefore have now x1 equal to minus tau j by b square ln of z. If but what is z? Z is tau minus bx2 by j plus j square by b square, z is tau minus bx2 by j plus integration constant, that is c. So this is therefore our equation which relates x1 with respect to x2. So we have got an equation, equation, a simple equation that only has two variables, x1 and x2. There is no time variable, so it was not directly possible to integrate this equation if we had proceeded with dx1 and dx2 only. So just to ensure that we get an equation that only has x1 and x2 on after solving this equation, so instead of directly using dx1 by dt, here we proceeded with substitution method, and you have actually already done integration via substitution methods. So now you have to plot this x1 with respect to x2. So you can take you have x2, you have x1, so you can take some value of x2 here while knowing what is the value of tau b and j. So if you take any quantity, say x2 equal to 1, you will find out what will be the value of x1 now. You will take x2 equal to 2, you will see what will be the value of x1. So you can use MATLAB to plot this x1 versus x2 graph using this equation that you have now obtained, this equation. So it has been seen what you'll see once you plot this system is once you will have a plot of this system, you will be getting curves like these. So for different values of constant of proportionality, you will be getting these curves for tau greater than 0, these are for different values of constant of proportionality, or you may get curves like these. For tau less than 0. And for different constant of proportionalities, these will be the curves that you will obtain for different, for whether tau is greater than 0 or whether tau is less than 0, and for different constant of integrations c. So this was another example how you can actually you have to actually mathematically be able to solve x1 dot and x2 dot, so that you get an equation that relates x1 with respect to x2. So whatever method you choose, however you proceed, you need to come up with an equation. You'll be given x1 dot and you'll be given x2 dot. You have to come up with an equation that will relate x1 with respect to x2. There will be no time in that equation. So this was about analytical method. Now we'll start the method of isoclines. So what we do in case of isoclines is we obtain we have the slope, we can obtain the slope of each point on the phase trajectory, and once we have the slope, uh, all the trajectories at every point on the trajectory, we can trace those paths to obtain the perfect trajectory or the phase trajectory of that particular system. So let us take a so say for example we have a system, a nonlinear system, which is uh, described by the equations x1 dot equal to x2 and x2 x2 dot equal to f times x1 comma x2. Fine. Therefore we can say dx2 by dx1 is equal to f of x1 dividing the second equation by the first equation. We'll be getting dx2 by dx1 equal to f times x1 by x2 divided by x2. Now what we were doing in the analytical solution is that we were solving this differential equation for obtaining an equation that would relate x1 with respect to x2. Now instead of solving this analytically, we can say dx2 by dx1 actually this equation refers or is refers to the slope of the tangent to the trajectory that can be that is actually alpha in this case. Fine. So the slope of the tangent to the trajectory, what will that slope be? That will be dx2 by dx1, or you can say that is equal to alpha. So which implies f of x1 x2 divided by x2 equal to alpha, or f of x1 x2 is equal to alpha times x2. Fine. Or you can say f of x1 x2 minus alpha x2 is equal to 0. So this all the trajectories that will be passing through any point on the curve will actually have the slope that is equal to alpha on the curve, and this is actually referred to as an isocline. So isocline is basically a locus of the points on the trajectory having the same slope. So we have actually seen that dx2 by dx1 when referred by f of x1 x2 divided by x2, we are getting this equation. Now depending upon whatever is f of x1 x2, we'll be getting a equation whereby we can determine for different values of slopes what equation it will be. Now that equation, this equation that we have actually obtained, this equation will not be the equation of the trajectory. This equation is actually refers to the this is actually the equation of the tangent to the trajectory. dx2 by dx1 is actually the slope of the tangent to the trajectory. So f of x1 x2 minus alpha x2 equal to 0. This is not the equation of the trajectory itself. This is the equation of the tangent to the trajectory whose slope is alpha. Now we'll find out for different values of alphas what will be these equations. So we'll be getting different tangents. So once we have different tangents, we can combine those tangents to get the portrait of the actual trajectory of the system that is described actually by x1 dot and x2 dot. To understand this, we'll take an example. So we have a system that's defined by x double dot plus x equal to 0. So let x1 be equal to x, that is actually one state of the system, and x1 dot will be equal to x2, fine, where once we substitute, what will x2 dot be? Therefore x2 dot is actually this term, that will be equal to minus x, that means actually minus x1. Therefore dx2 by dx1 is equal to minus x1 divided by x2. So we have obtained dx2 by dx1 equal to minus x1 by x2 equal to alpha, where we to assume that alpha is the slope of this tangent to the curve. Therefore minus x1 by x2 equal to alpha means minus x1 equal to alpha x2, where x1 plus x2 alpha x2 is equal to 0. Or you can also say this is x1 equal to minus alpha x2 plus 0, fine. That is actually comparable with y equal to mx plus c. So this is actually an equation of a straight line where slope is actually minus alpha, not plus alpha. So if we are taking so once we plot this, we need to take that thing into consideration. So now what we have obtained is x1 equal to minus alpha x2 plus 0. So take for alpha equal to minus 1, x1 will be equal to x2. That means we have a straight line corresponding to alpha equal to minus 1. Corresponding to alpha equal to 1, we have x1 equal to minus x2. Or you can say x2 equal to minus x1. So again we have a straight line alpha equal to 1. At alpha equal to 0, x1 is equal to 0. That means it is actually a straight line along this y-axis. So this is alpha equal to 0. Alpha equal to minus 0.5. Alpha equal to plus 0.5. So you can take different values of alpha. It's not necessary you take these values only that I have shown here. So these are the straight lines that who have whose their slope is equal to alpha. We need to be able to so these actually represent the equations of those tangents. Now what we'll be doing after this is take any point on this curve so we are taking a point on this curve. We know the slope of this curve is alpha equal to 1. So draw a straight line whose slope is equal to alpha equal to 1. So alpha equal to 1 means a straight line like this. Fine. Take another curve, take another line whose slope will be equal to the slope of the line that is coming after this, that is actually in this case alpha equal to 0.5. So alpha equal to 0.5 means a straight line like this. Fine. So this is a curve whose slope is equal to alpha equal to 1. This is a curve whose slope is equal to alpha equal to 0.5. And why we are taking 1 and 0.5? 1 is actually the slope of this particular straight line, and 0.5 is the slope of the line that will be coming after this. Now whatever is coming in between these 2 points, trace that path I'll take that, show this here, in between up to the next line. Fine. So this is what I have done. So now I have this particular point on this curve. Draw again a straight line whose slope is equal to 0.5. That is actually this particular slope of this particular curve. And after this we have a curve whose slope is equal to 0. So draw that. This is alpha equal to 0. Fine. So in between, whatever is passing through in between, trace that path up to the next point. Similarly, at this point, draw a slope that will be equal to alpha equal to 0, and draw line that will be equal to alpha equal to 0 minus 0.5 in between जो भी path आएगा. Trace that, keep on doing this, so the greater the number of points you will take, so better this will look. So approximately we are drawing an approximate curve, so it will look something like this, approximate curve. Fine. So if you have a number of straight lines and you will find out slope at alpha equal to 2, alpha equal to minus 2, alpha equal to 3, alpha equal to minus 3. So once you will trace that path, you will actually get a perfect circle. Fine. So instead of obtaining a graph like this that I have obtained, that is still a closed loop, you will get a perfect circle. So you can take a number of points. You can take a point here, then start tracing it. Take one line that is equal to alpha equal to 1, another line alpha equal to 0.5. उसके बीच में जो भी curve है, trace that. Keep on doing this. Keep on tracing these paths. So you will keep on tracing these paths. You will end up getting the phase trajectories. So this is how you plot a phase trajectory. Now this is the phase trajectory of the system. These lines that we obtained, these yellow lines, these are the isoclines. These represent all those tangential paths whose slope is equal to alpha. So this is how you can plot a phase portrait using the method of isoclines. One, you have to first of all equate your dx2 by dx1 equal to alpha. So if whatever equation you are getting, this will not necessarily be always a straight line. It can be a different, say for example, dx2 by dx1 would have come out to be minus x1 square by x2. So it would have been a parabolic equation. So in this particular case, it is simple. So y equal to mx plus c, or x1 equal to minus alpha x2. Take different values of alpha, you will get different straight lines. Then take a point on that straight line. At that point, take two different curves having alpha slopes alpha equal to alpha will be the slope of that particular line, and another curve will have slope of the line that will be following it. So you'll be doing this thing and you'll be tracing these paths. You will end up with these trajectories that will actually represent the phase trajectory. Once you have a number of these phase trajectories, that will form your phase portrait. So this was a simple example wherein we are getting a circular trajectories. This is something that we have already actually done in this equation. With there also we had obtained circular plots, so we are also obtaining circular plots here also. So using this method, we'll try to plot some different curves for different nonlinear systems in the next session.